Good morning and good afternoon, everyone. This is George Kadifa. This is one more talk in our technology series at Sumeru Equity Partners. Today, we're very pleased to have Alan Baratz with us. Alan is President and CEO of D-Wave, the leader in quantum computing. I've known Alan for several years now. From the days where he was part of inventing what is now what is Java is at Sun Microsystems, also all the way that when he had leadership positions at Cisco and Avaya and other places. And without further ado, just wanted to introduce Alan, and he has a presentation for us on quantum computing. Alan, please.
Great. Thanks, George. Thanks for the introduction, and thanks for the opportunity to be here today and to spend some time talking about quantum computing. As George said, I'm the CEO at D-Wave Systems. I've been with the company for about 3 years now. Prior to that, I've been a senior executive at a number of large companies, as George said, Sun Microsystems, Cisco, Avaya. I've also been a startup CEO multiple times, and I've been a venture investor. I was with Warburg Pincus, and I opened their first California office. So I've had an opportunity to see technology from all sides of the table. And I will tell you, quantum computing technology is one of the most exciting technologies that I've had the opportunity to be involved with. Typically, when I talk about quantum computing, the first question that I get asked is, when will quantum computing get to the point where I can do something useful with it? Or when will it make a significant positive impact on my business? And most people will tell you that we are 5 to 10 or more years away from that. I'm going to tell you that the answer to that question is today, that quantum computing has reached the point where today you can run real business applications at commercial scale. Now, that's a unique position that I have coming from D-Wave, because we actually are the only company that provides a quantum computer that has the ability to do that. And I'm going to spend some time talking about quantum computing in general and the quantum computing landscape. And then I will dive into what we do at D-Wave and why we're at the point where we are versus some of the other players in the space. Recently, a research firm, 451 Research, it's affiliated with the S&P, did a survey of Fortune 1000 enterprises, essentially trying to find out what their interest is in quantum computing and where they are with respect to thinking about applications of quantum computing. And what they found was that 4 out of 5 of the companies they surveyed said that they have a use case in mind for quantum computing sometime within the next 3 years. But almost 40% of them said that they're actually working with a use case for quantum computing today. And even more interesting, almost a third of them said that there are problems that are important to them that they need to solve, but they've had to abandon because classical computing just isn't powerful enough to be able to support the solution to those problems. And so all of that actually bodes quite well for quantum computing and is kind of the backdrop for my question initially about when will quantum computing be able to create value and why do I think that today is the time for that. Let me take a step back though and talk about what is quantum computing. I'm going to start at a very high level, but I'll go into a bit more detail, and we can do more of that in Q&A if you'd like. But typically, when somebody asks what is quantum computing, the answer that they get is the following. Typical computers encode information in bits, and a bit can take on a value of 0 or 1. And then you apply a sequence of instructions to those bits to compute solutions to various problems. Well, the interesting thing about quantum computers is that the information is stored in qubits rather than in bits. And the qubits can take on the value of 0 and 1 simultaneously. Actually, what's going on is that they're taking on some percentage of a 0 and some percentage of a 1. And at any instant in time, they're actually taking on all percentages of 0 and 1. And what this means is that at any instant in time, they can see all possible solutions to a problem. And it really is this, in some sense, infinite parallelism that gives quantum computing the power that you often hear about. There are two primary approaches to quantum computing, or two architectural approaches to quantum computing. They are known as annealing quantum computing and gate model quantum computing. And as you'll see from this chart, almost everybody other than D-Wave is focused on gate model quantum computing. Those focused on annealing are D-Wave, a little bit of work in the US government, and NEC, but NEC is focused on it because they're a partner of D-Wave's. So why is it that almost everybody is focused on gate model quantum computing? The answer to that question is that there's a fair amount of mathematical and physics theory that underlies gate model quantum computing. And in particular, there's a theorem known as the threshold theorem, which states that if you can achieve a certain very low error rate in your computation, then essentially you can build think of it as deterministic quantum computer. And at that point, you can prove that certain types of problems can be solved exponentially faster on the quantum computer than they can be solved on classical computers. And some of the examples of this are Shor's algorithm for factoring large semiprimes. I mean, typically, you'll hear that quantum computers are going to break all the cryptography schemes that are in existence today. And in fact, it has been shown that that could happen. Although in order for that to be a reality, you need to achieve the threshold that's defined in the threshold theorem. And most experts believe that we are 10 plus years away from that. So we've got quite a ways to go before we really have to worry about cracking RSA. But nonetheless, it is that mathematical underpinning that has most companies focused on gate model quantum computing. The same mathematical underpinning does not currently exist for annealing quantum computing. Annealing is probabilistic in the sense that when you submit a problem to an annealing quantum computer, you will get a solution back, and you will get the optimal solution with some probability. Now, what is good about annealing quantum computing is that it is much easier to scale, and it is much less sensitive to errors. And so it's possible to build large annealing quantum computers with low enough error rates that you can actually do useful work with them today, but we can't yet formally prove anything about the difference between annealing quantum computing and classical computing. And so it's more try it, benchmark it, see what kinds of results you get. Now, that having been said, I will tell you that while this quantum computer that reaches the threshold is typically called a universal quantum computer, frankly, today there is no universal quantum computer. Neither the annealing quantum computers nor the gate model quantum computers are universal. The annealing quantum computers are not universal because the nature of the qubits is such that they don't allow for all possible three-dimensional orientations of spins in the qubits. Gate model is not universal because the error rates are too high. We haven't crossed the threshold theorem yet. And so today, all quantum computers are probabilistic. whether you look at a gate model quantum computer or you look at a annealing quantum computer, they're all probabilistic. None of the theory applies today. And as a result, all you can do with quantum computers today is try to run an application on it and see what kind of results you get and compare them to classical to see if you're getting anything of value over classical. So apples to apples, annealing and gate model are the same today, except for the fact that annealing quantum computers are much larger with 5,000 qubits versus gate model with 50 qubits, and they're much less sensitive to errors, so they can do useful work today, which can't be done on gate model systems today. As we look to the future, obviously, on the gate model side, there's a lot of work around how to reach the threshold so that we get a universal error-corrected gate model system. But on the annealing side, it's also been shown that it is possible to construct a universal annealing quantum computer that does have all the same properties of a universal gate model quantum computer. In fact, the two are mathematically equivalent. And so at D-Wave, as we continue to increase the size of the quantum computer, reduce the noise and the error rates, while we're not universal, we are doing that on the path to a universal annealing quantum computer. And then the interesting question is, who will get there first, gate model or annealing? I have my view, but I'll leave it to you all to decide what you think. Just as an example of the scalability of annealing versus gate model, in the last 15 years, gate model systems have grown from 9 qubits to a whopping 50 qubits. In fact, most of them are 20 to 30 qubits. Over that same period of time, the D-Wave annealing quantum computer has gone from 2 qubits to our most recent system, our advantage quantum computer, with over 5,500 qubits. So this is kind of a concrete view on the fact that annealing is a much easier technology to build and a much easier technology to scale. Moreover, if you ask about the commercial readiness of the various quantum computers that are out there today, I can point you to some work that was done by the Jülich Supercomputing Center in Germany, where they've defined a quantum technology readiness scale, much like the standard technology readiness scale, from level 1 through level 9. And they've evaluated many of the quantum computers that are out there in existence today. And you can go to their website to see this research work, but basically they've placed D-Wave at readiness level 8 and everybody else at readiness level 5 or below. And you can see that just to go from 5 to 6, you need error correction. And most people believe that that's what's 10 years away for gate model quantum computers. The reason why D-Wave has already passed that is because, as I've said, the D-Wave system is just less sensitive to errors. And so we do not need the same level of error correction in order to be able to do useful work. So what about the performance of the D-Wave quantum computer? Is it any better than classical? So about 3 years ago, some work was done, actually not at D-Wave, it was done by a researcher by the name of Helmut Katzgraber, who had been, I think it was a university in Texas. I think it was Austin. I'm not 100% sure. He then went to Microsoft. He's now at AWS. But basically, Helmut showed that there was a class of synthetic benchmark problems. He called them deceptive cluster loop problems, which could be solved on the D-Wave quantum computer about 100 times faster than they could be solved classically. So, this is certainly not an exponential speed up. It's not a scaling speed up where the distance between classical and quantum grows as the size of the problem grows. But nonetheless, it was still a speed up. The reason why these were called deceptive cluster loop problems was because they had constructs inside of them that the classical algorithms had to find in order to be able to solve the problems efficiently, and they were just very hard to find. Okay, so that was 100x speed up on a synthetic benchmark problem. About a year and a half ago, we did some work on simulating a phase transition in a magnetic material. This was known as the Kosterlitz-Thouless phase transition, or the KT phase transition. The physics behind this transition won the Nobel Prize in 2016. And this is very, very difficult to simulate classically. And what we were able to do was simulate this transition on a two-dimensional magnetic material lattice on the D-Wave quantum computer and show that we could simulate it 3 million times faster than it could be simulated classically. So now we've gone from 100x speed up on a synthetic benchmark problem to a 3 million x speed up on a real world physics problem. Okay, that's all fine and good, but what does that mean for commercial problems? And that's, in some sense, where we are today. It's, do we have the ability to actually solve commercial problems at production scale better than they can be solved classically? Well, what we are focused on is, can we solve them better than our customers are currently solving them? We don't call that quantum supremacy. We don't call that quantum advantage. We call it customer advantage. Can we deliver an ROI for the customer as a first step toward commercializing quantum computing? And to date, about 250 early applications have been developed on the D-Wave system. These are real business applications, although most of them running at a relatively small scale, not at the scale at which they could be used in production to support a business. However, with the launch of the Advantage system, and we launched that at the end of September, so about 2 months ago, and a new hybrid solver that we introduced at the same time, we actually now are able to solve many of these problems at production scale. And I'll talk about that in a few minutes. Okay, so this is simply a prettier picture of the curve I showed you previously, which shows the various D-Wave quantum computers that have been brought to market over the last 10 to 15 years, starting with the D-Wave 1, which had about 500 qubits, the D-Wave 2 at 1,000, the D-Wave 2000Q, which was 2,000 qubits. That was actually the system that we've had in the marketplace up until last September. And then the new Advantage system with over 5,000 qubits. That new Advantage system pictured here, as I said, has over 5,000 qubits, so over double the number of qubits of our previous generation system. In addition, each qubit is connected to 15 others. That's also over double the connectivity, because each qubit in our 2,000 qubit processor was connected to 6 others. So we've now gone from a system with 2,000 qubits and degree 6 to a system with over 5,000 qubits and degree 15. So that's over double the connectivity and over double the number of qubits. The combination of these two factors means that we can now natively solve problems about 3 times as large as what we could solve on our previous generation system. And I'm going to give you a metric that puts that into context in just a minute. But this is a real science and engineering feat. This is a superconducting system. So our chip is superconducting. It runs at about 10 millikelvin. It has over 1 million Josephson junctions, which makes it the largest superconducting chip ever developed. Moreover, we've been able to scale this processor without increasing the time to program it, without increasing the time to read out the solution, and without increasing the temperature at which it runs, all critical, which means we have been able to scale the technology, and we don't see any impediments to continuing to scale the technology into the future. But it's also not just about the systems, it's also about the software. And I'm going to talk about that in just a few minutes, because it's the combination of the two that really gets us to real business application scale. As far as a system roadmap is concerned, we haven't announced this yet. So, you know, these charts are marked confidential. I mean, we don't have a confidentiality agreement in place, but, you know, I'd appreciate it if you not, you know, spend a lot of time talking about this externally. But our next generation system will be out in about 2 years, and it will have over 7,500 qubits and most likely degree 22. So again, going from 5,000 qubits now to 7,500, going from degree 15 to degree 22. 2 years after that, we will bring out a system that uses new materials that have a very significant reduction in noise and error rates and a huge increase in coherence times, which will allow us to do something that's called coherent annealing. Right now, we are not coherent. Our qubits are not entangled for the full duration of the execution of the application. However, with coherent annealing, we would be coherent, we would be entangled for the full duration. And that will be a significant milestone for us, at which point we actually provably will be able to do something that quantum Monte Carlo cannot do. We won't be able to say we can provably do things that can't be done classically, but we will be able to say we can provably do things that can't be done by quantum Monte Carlo, which is typically the algorithm of choice for the types of problems we solve. And this is all on the path to the universal annealing quantum computer. Just to give you, just to put our performance improvement, you know, system over system, year over year into some context. You know, if Moore's law were to continue, we'd be talking about 2x performance improvement about 18 months. D-Wave is actually on 100x performance improvement every 2 years. We've demonstrated that over the last 10 years, and we believe that that will continue into the future. And it has to do with a calculation related to both noise reduction and increase in qubits and connectivity. And we have a pretty high degree of confidence in that 100x improvement every 2 years. Moreover, and this is a really interesting point, we use very little power. In fact, because the chip is superconducting, the chip itself consumes no power. All the power for this system is the power required to run the refrigerator. And we can actually put multiple chips inside a single fridge. So our system requires about 25 kilowatt hours. And you know, we've done some analysis on various different types of problems. We were able to show that our 2,000 qubit processor could compute various problems with about 100x less power than a GPU farm to solve in the same amount of time. With the new Advantage system, that improvement goes to about 10,000x less power. So, you know, there's also kind of an ESG story here, but these systems also are very power efficient. Okay, I said a minute ago that it's not just about the systems, but it's also about the software. You know, our quantum computers, including our new Advantage system, and we also have one of our older 2,000 qubit systems, are all available within our quantum cloud service. It's called Leap, and anybody can get access to Leap. You go to our website, it takes about 30 seconds, and you have access. You get a minute of free time. If you're willing to open source the work that you're doing, you can renew that minute every month. And a minute of free time can allow you to run between 400 and 4,000 problems. So it's not a trivial amount of time on the quantum computer. And you get true real-time access to the quantum computer. You submit a job, it's queued, it runs, you get results back. In fact, the D-Wave quantum computer is the only quantum computer on which you can get real-time access. In all the other cases, you either need to schedule a block of time or you submit the problem, it's run, and you're informed. You know, it's run by the owner of the system and you're informed when the results are available. But D-Wave is queued true real time. However, inside of Leap, is what we call a hybrid solver. So you can run jobs directly on the quantum computer, or you can run them through the hybrid solver. The hybrid solver uses a combination of classical resources, CPUs and GPUs, running in combination with the Advantage processor to be able to solve problems much larger than what can be solved natively on the quantum computer. This is what has allowed us to get to commercial scale. And just to give you a metric to help with that, on our 2,000 qubit quantum computer, we could solve problems with on the order of 100 to 200 variables. With our new Advantage quantum computer, we can solve problems with on the order of 600 to 800 variables. If you use the hybrid solver backed by the Advantage quantum computer, we can now solve problems with up to 1 million variables. In addition, we have introduced two versions of this solver, what we call a binary quadratic solver and a discrete quadratic solver. In the binary quadratic solver, those variables need to be binary variables, taking on a value of 0 or 1. In the discrete quadratic solver, the variables are discrete variables, meaning they can take on a value from a set of possible values. So for example, one of the numbers in the set 1, 2, 3, 4, 5, or one of the colors in the set red, orange, yellow, green, blue. The reason why this is important is because some problems are inherently binary, some problems are inherently discrete. Previously, if you had a discrete problem, you had to convert it to a binary problem. Now you no longer have to do that. We have a hybrid solver that will support that. Okay, as far as our Leap cloud service is concerned, as I said, it gives you true real-time access to the quantum computer, but it gives you much more than that. We have demos, we have reference examples and application templates that make it easy to get a quick start. We have a full developer environment integrated into it, fully configured with our open source tools so that you can start writing code immediately. It's all Python based. And so you can basically pull one of the templates into the developer environment and start modifying it to look more like the problem that you want to solve. We have training materials, and we have a community section where developers can meet one another, ask questions, and get help solving their problems. As I said, one of the key elements of the Leap service is the hybrid solver. So you can submit problems not just natively on the quantum processor, but also through the hybrid solver. As far as the performance of the hybrid solver, HSS is the term that we use to refer to this, the hybrid solver service. We've done a fair amount of benchmarking of the hybrid solver service against various classical heuristics on a broad array of problems. Remember, I said these are probabilistic systems, and really what the name of the game right now is to compare to classical and see if you're getting a benefit. So what we've used is an open source repository called MQLib that's maintained by MIT. This is a fairly large set of optimization problems, which is what our system is quite good at. And typically what MIT does is they try to solve these problems using a set of classical heuristics, the best out there, but a large set of them, 27 in fact, and then they publish the results. And so what we've done is we've run 45 of these applications on our system through our hybrid solver and compared the results to the best of the classical heuristics. And what we found is that on almost all of the problems, we are better than the best of the classical heuristics, and in many cases, significantly better than the best of the classical heuristics. Okay? I mentioned our open source tool suite. We call it Ocean. So those are, in some sense, our 3 product families: Advantage for the quantum computer, Leap for the cloud service, and Ocean for our open source software development tools. These are fully integrated into the developer environment inside the Leap cloud service, or you can download them, install them on your system, configure your own developer environment, and then submit jobs back up to the quantum systems through Leap. So you can either develop inside of Leap or develop on your local system. What's nice about the Ocean tool suite is that you can do your development at 3 different levels of abstraction. So At the highest level, we basically provide solvers for various different types of applications. For example, we provide a solver for constraint satisfaction or satisfiability. We provide solvers for various classes of graph problems and the like. That's at the highest level. So, if your problem is, for example, a maximum independent set problem, like say you're trying to do antenna placement and it translates into an independent set problem, you don't have to know anything about the quantum computer or the hybrid solver. All you do is create the graph for your independent set problem and call the independent set solver, and we'll solve it and send you back the results. That's at the highest level. At the lowest level, if you want to set the biases on the qubits or on the couplers, if you want to use various esoteric features like reverse annealing or spin reversal transforms, we provide the interfaces to control all of that on the quantum computer. And then in the middle, maybe we don't provide a solver for a certain type of problem, but at the same time, you don't want to have to worry about, managing all the individual hardware components. We provide a level of abstraction that allows you to create a new solver, and then we map it into the hardware underneath. So three levels of abstraction for the tool suite. Okay, so what are some examples of how our system has been used? And as I said, we really have just now crossed the threshold to the point where we actually can now support real business applications at commercial scale. And let me give you a couple of examples. Save On Foods. Save On Foods is a grocery store chain up in Canada, fairly large. We worked with Save On Foods through the beta program for Advantage Quantum Computer and the new hybrid solver. And we've been able to develop an application to optimize a portion of their logistics. And we are able to solve that problem that used to take them 25 hours a week to solve. We solve it in 2 minutes for them. So real business value. They've just started rolling this out, and over the course of the next 3 to 4 months, we expect it to be rolled out across their entire environment. Another example, actually not on this chart, is Volkswagen. Volkswagen has used our system for a number of years now. They originally started doing global traffic routing with the system. And so unlike Google Maps, where I want to get the shortest path or the shortest time path from my home to my office, which is a very easy problem to solve computationally, what they're looking at is I want to simultaneously and in real time route all the vehicles in a geographic area to minimize congestion overall in that geographic area. Now, that is a much harder problem to solve. That's what's known as an NP-hard problem, an exponentially hard problem. The computational effort required to solve it grows exponentially with the size of the problem. And they've been able to solve that problem leveraging our system. And in fact, they had a little bit of fun with it at the web forum meeting a year ago, where they used it to route the buses for the web forum summit meeting. It was special purpose hardware that went into the buses, that mapped up to their cloud service, that communicated with our quantum computer and hybrid solver on the back end. And it was kind of fun. One of the bus drivers actually said, this thing told me to take a route that I would never have taken, but it was right. So, okay, fine, some nice anecdotal evidence. But Volkswagen now, with our new Advantage system, is working on optimizing some of the elements of their manufacturing process. And they've started with the tail end of the manufacturing process, which is vehicle painting. It's an application that they call paint shop scheduling. And the idea is you want to create a schedule that minimizes the paint changes in the paint shop, because every time you do a paint change, you have to change and clean nozzles, and there's a fair amount of waste that occurs when you do that. And what they did, again, through our beta program working with us, is that they found that they were able to come up with schedules that result in 80% less waste than what they were seeing in the schedules that they were using based on classical computation. And so they're now in the process of rolling that out for manufacturing. Another example is a small company called Menton AI. Menton works on de novo protein discovery. So basically creating new proteins for drugs. And leveraging our system, again, through the beta program, they've developed 10 new proteins that are in synthesis that will likely go into trials for new COVID therapeutics. Now, they've done a really interesting experiment here. They also created some new proteins classically. So it's a combination of the time and the quality of the proteins that come out of the system. We ran faster, and now they're evaluating the various different proteins to see which were better. So we're kind of waiting on that, but so far they're pretty excited by the results. And there are other examples. OTI Lumionics does OLED materials development, and they have a computational chemistry platform that uses our system to compute properties of molecules. Denso is using us to do scheduling of robots on a plant shop floor, and so on. So, look, D-Wave quantum computers, annealing quantum computers cannot solve all quantum problems. You do need a universal quantum computer, for example, to solve Schrodinger's equation and quantum chemistry problems. However, what we can solve is optimization problems, and most businesses run on optimization problems, and a number of problems related to optimization, like satisfiability problems and material simulation problems. And so, everything from commercial optimization to molecular discovery, fault diagnosis, cybersecurity, not cracking encryption, but things like threat detection. These are all application areas that can benefit from the approach to quantum computing that we've taken. And of course, as we look to the future and move to coherent annealing and move to universal quantum computing, then that opens up the opportunity to not just kind of improve business operations, but to transform businesses and frankly the way we live. As we start looking at things like designer drugs targeted to individuals, or autonomous vehicles and global climate modeling and the like. So we're at a really interesting point in time for quantum computing. I think that there's been a realization on the one hand that the gate model approach to quantum computing is going to take a lot longer than anybody thought to be able to deliver any real value. And so there's a lot of research that needs to be done in that area. We're probably talking 10 to 15 years before you can get any real value. And it's an open question as to whether you'll be able to get any value before then. On the flip side, for us at D-Wave, we're already supporting commercial applications. We have over 18,000 developers that are signed on to our Leap Cloud service, with over 1,000 of them regularly using the system. We've got a partner network that we've developed. For example, Accenture is a partner of ours in helping customers to build applications that run on our system. AWS is a partner of ours. We're part of the Bracket cloud service. We work with a broad array of startups. We're actually involved with an organization called the Creative Destruction Lab. It began out of the University of Toronto in Canada. It's a really interesting mentoring program for startups. There are, frankly, 40 or 50 mentors that participate in the program, a couple of hundred investors that participate in the program, and every year a new cohort of startups is selected in a number of different areas. One of the streams is the quantum stream, and basically it's roughly an academic year program with meetings every 2 months, where you essentially you mentor these startups to be successful. At the beginning of a 2-month period, you set goals, you mentor them through the 2-month period, you review where they are at the end of the 2 months, set goals for the next 2-month period, and so on. It now runs at several different locations across Canada, and it's also running in Europe, and there may be one in the US. I'm actually not sure at this point. So a lot of interesting work going on. We think from a D-Wave perspective, we're at a really good point in time. So that's really what I had intended to share with you. We have about 15 minutes left, and so I'll open it up for questions. And maybe I'll stop sharing my screen.
So it looks like we don't have any questions right now, Alan, but anyone in the audience, if you have any questions for Alan, you're more than welcome to add that into the bottom of your screen, and Alan and George will go through them.
And actually, sorry, go ahead.
Yeah, and Suyen, they just, just to let them know, so they click on the QA button down, correct, and then they type their question. How should they do that?
Yes, there should be a little bar at the lower right-hand corner of the Zoom window, and you should be able to just click into that and type in your question.
Hey, George, maybe I can just ask a question verbally while we type things.
Oh, please do, John.
Yeah. So, Alan, typically when you read about quantum computing, the boogeyman of sort of what it will mean to the cryptographic foundations of modern computing, privacy protection, all of those things are raised. Some people push it aside and say it's not important. Others say it's a real hazard and everything's going to have to be rethought. Can you just take a few minutes and provide some more insight there?
So first of all, it absolutely is a hazard. It's just that it's not an urgent hazard. And what I mean by that is, as I said at the very beginning, it has been mathematically proven that a universal quantum computer can break RSA. And in fact, most current cryptographic schemes. Now, in order to do that, though, you need a universal quantum computer and you need a fairly large universal quantum computer. For example, if you wanted to factor a 2000-bit semi-prime, which is kind of what you'd want to target if you're trying to break RSA today, that would require about 4 million qubits. So think about that. We're currently at 50 gate model qubits, 5,000 annealing qubits. We would need to get to 4 million, and we would need full up error correction. As I said, most people believe that we are 10 to 15 years away from having real error-corrected universal quantum computers, but it isn't even clear if in that time frame we can get them to be as large as 4 million qubits. So while it is a real threat, it's not a threat anytime soon. And so we absolutely should be working on quantum resistant and polymorphic cryptographic schemes to be ready when quantum computers exist that are a threat. But we've got time. Now, the other piece of it is how long it will take to actually convert over to the new schemes. And so, that's why it's important to start working on it now. And it's important to make sure we have enough lead time to do the conversion before we get systems that are actually capable of cracking the cryptographic schemes.
That's really useful. Thank you. Because if you were just to read the popular press and the Twitter stream, you would think it's an item that's around the corner. And I think your view is one that it's coming down the road, but there's certainly time to prepare for it.
I will tell you, the largest semi-prime that's ever been factored on a quantum computer was actually factored on our system, and it was about 20 bits. And our new Advantage system will be able to go to 30 bits. So, and here we're talking about trying to get to 2000 bits.
Right. Okay. Great. That's super useful. Thank you. George?
Yeah, thanks, John. Any additional questions for Alan? Maybe I'll have my own question also, Alan. You talked about Moore's law, and we all are getting to a point where Moore's law actually is starting to flatten, especially with 7 nanometer technology. Anything beyond that at this stage becomes very, very difficult to scale. Is quantum computing the next technology to keep Moore's law alive, or how should we think about it?
Yeah. So first of all, since you mentioned technology, I will tell you that currently at D-Wave with our superconducting chips, we use quarter micron technology. So we are not at all state of the art on the underlying technology. We are superconducting, and that makes us state of the art, but we've got lots of room to grow. Now, but that isn't quite the question you were asking. So, the way you need to think about quantum computers is not as replacements for classical computers, but as coprocessors. Think of them more as GPUs, where you would offload the hard core of the problem. So I would never try to run a user interface on a quantum computer, right? But the kind of exponentially hard compute in the core of the application, that's what I'm going to offload to the quantum computer. And so, to the extent that, we're talking about things that, are better done on classical, no, quantum computers are not going to be the answer to the flattening of the curve on Moore's law. But if the reason why you're worried about the flattening of the curve is because you're worried about that hard computational core, then yes, quantum computers will be able to help out in that area.
Great. Thank you. There are a couple of questions that just got posted there.
Yeah, I see them. So the first question is, now I know, George, did you want me to say who asked the question or just ask the question, or just repeat the question?
Whatever works for you.
Okay.
We're flexible.
The first question from Ben Cox. I'll say the name as long as I can pronounce the name. What kind of problems do you see quantum computing solve in software development? So, first of all, again, it always goes back to the hard computational core of a problem. So to the extent that, for example, in testing, there are various graph problems that you use to model the code and to evaluate the code. And these graph problems are hard computational problems, NP complete many times. That's the kind of thing that you might look at using a quantum computer to help solve. Again, if we're looking at things like, how would I do scheduling of a large software development effort? Again, scheduling problems tend to be hard computational problems. I mentioned Save on Foods. I said logistics. It was actually a specific scheduling problem for them that we ended up solving. Again, that's the kind of place where it might be used. So really what you're looking for is the parts of the application or the problem that have a very complex computation involved. Okay, the next question is from Nathan Sanley. When can we expect to see quantum computing applications in consumer tech? So, okay, so this is kind of interesting. We did some work with Google actually a while ago. They basically wanted to put some image recognition into Google Glass, and they wanted to do it through, essentially a neural network, and they had to do some learning on that network. And they used our system to do the learning, and they were able to come up with a much more compact network than what they had been coming up with doing the learning classically. And so while unfortunately, Google Glass isn't with us any longer, that's kind of an example of the use of quantum computing in consumer tech. So look, I don't think anytime soon there'll be a quantum computer on every desktop. And even though I said it's kind of a coprocessor like GPUs, I also don't think anytime soon we'll have plugins to our desktop systems that are quantum. I think we'll get there, but I think again that's more like the 10 to 15 years out. For the foreseeable future, these are going to be systems that are going to live in data centers and they're going to be accessed over the cloud. And it's always back to, okay, what is the hard problem that you're struggling to solve classically? Another area that probably has some applicability to consumer tech, anything machine learning. So, a minute ago I said that we did some work with Google on actually training. We're not fantastic at training. I don't know that I would actually use us over GPUs to do training. Although in that particular case, we did do quite well. But what we are good at is something called feature selection. And so this is a case where you've got many, many different features. And what you want to do is you want to select from that a small number of the best features to train on. And that is a hard optimization problem. It's a binary quadratic optimization problem, which is an NP-complete problem. And we are quite good at that. And we have been used many times. So, to the extent that for a consumer product, you're trying to create a machine learning model and, you've got more features than you can actually train on efficiently, and you want to do some feature selection, that might be a place where you could use a quantum computer today to get some benefit. Okay, and George, I don't see any other questions in the chat.
We're almost approaching the hour. Alan, a concluding question, unless someone still has any questions, which is, it's now 2025 and you're back with us. What would we see then? What would you talk about at that point?
So 2025. Okay, so first of all, and I need to say up front, I'm going to give you a biased answer. Right? It is what I believe, but I'm answering it through my eyes, my view of where things are and how they're going to materialize. I do not think that we will be much further along on gate model quantum computers. Even you look at IBM and they say they're trying to build 1,000 qubits, right? But remember, in order to get one error-corrected qubit with a superconducting gate model system, you need 1,000 physical qubits. So what they're trying to build, I think they've said a year. I'd be surprised if they get it in less than 2 to 3 years. You would be seeing 1,000 physical qubits giving you one error-corrected qubit, which you can't do anything useful with. Psi-quantum, they use photonics, says that they'll be at, I think some number 500 maybe error-corrected qubits in 5 years. But if you really push them on it, they will tell you that they don't really think that system will be broadly applicable. And they'll, when they get there, they'll have to see, how high quality it is and whether or not they can actually solve any real problems. So I think in the 5-year time frame, you'll see advances on the gate model side, but I think we'll still be talking about relatively small numbers of qubits, less than 1,000, and we still will not have achieved true error correction. And so I think, these things will still be relatively small, they'll still be very error prone, and it will still be difficult to do anything useful. At the same time, on the D-Wave side, in the 5-year time frame, we should be at 10,000 qubits. We should have connectivity in the range of 20 to 25, each qubit connected to 20 to 25 others, and we should have coherent annealing, which will have us at the point where, we can provably solve some very, very hard problems better than classical. But I'm talking real problems, either in the physics arena or in the commercial arena. So, but as I said, that's a biased view, and I run D-Wave, and I think you'd be surprised if I said anything other than that.
Well, if I had to bet, I'll bet on you, Alan. Again, thank you very, very much. We really appreciate you spending your valuable time with us. With that, I think we're concluding, and thank you again.
My pleasure. Thank you all for the time.
Thanks.